As climate change intensifies, coastal cities face a relentless enemy, the destructive power of the rising ocean. Colossal waves and rising sea levels threaten to erase centuries of human infrastructure in a single surge.
To protect millions of lives and trillions in assets, American engineers are building the most fortified seawalls in history. This is a sophisticated blend of civil engineering, hydrology, and advanced material science.
Every meter of a seawall is the result of thousands of hours of tidal force and wave pressure simulations.
The process begins by preparing the underwater foundation using massive industrial dredging vessels. A specialized geotextile fabric is laid down to prevent erosion and the sinking of the wall's sand foundation. Massive steel sheet piles are driven dozens of meters into the seabed to create a high-strength structural skeleton.
Professional dive teams and remotely operated vehicles inspect every centimeter of the foundation beneath the ocean surface.
Millions of tons of large armor stones are transported to create the primary underwater cushioning layer. Precision is vital to creating a structure capable of neutralizing the energy of violent waves.
Modern seawalls are not just flat blocks. They are complex geometric structures designed to reflect energy.
This specialized concrete is engineered to resist saltwater corrosion for over a century. Smart sensor systems are integrated to monitor the wall's stability during major hurricane events.
To enhance protection, engineers utilized specialized geometric concrete blocks to break wave energy. These tetrapods are masterpieces of engineering, allowing water to pass through while neutralizing impact force.
The manufacturing of these blocks occurs at coastal plants with absolute geometric precision.
Massive production scales ensure enough material to cover dozens of kilometers of vulnerable coastline. Now, let's go deep into the technical casting and installation process of these ingenious concrete units.
Underwater excavation is the first step, removing unstable silt to reach the solid bedrock.
Clean aggregate is sorted to create a leveled bedding layer for the massive wall structure. Automated leveling systems ensure the foundation is flat to within a few centimeters. In high surge areas, the wall is literally bolted to the earth to prevent it from sliding.
Environmental protection measures, like bubble curtains, are used to safeguard sensitive marine ecosystems.
Geologists analyze the rock's strength to calculate exactly how much weight the seabed can support. Real-time sonar imaging provides engineers with a digital twin of the underwater terrain. Steel templates are used to ensure that the primary structural piles are perfectly vertical. Vibratory hammers use high-frequency resonance to sink steel piles into dense sand layers. These piles form the deep-rooted fingers that lock the wall into the earth.
The piles are welded together to form an interlocking, watertight barrier.
Anti-corrosion coatings are vital for materials exposed to the constant salt spray of the ocean. Smaller filter stones prevent the foundation sand from being sucked out by the retreating waves.
Every rock is placed according to GPS coordinates to build the exact slope required for wave breaking.
The rock mound grows layer by layer, forming the massive core of the breakwater.
Water quality is monitored constantly to ensure construction does not harm local coral or fish.
Operations continue 24/7 to take advantage of low tides and calm sea conditions.
The foundation is now ready to support the heavy concrete armor that will face the waves. With the ground prepared, the factory on land shifts into high gear. The recipe for marine concrete is a closely guarded secret of chemical engineering. At the casting center, high-grade concrete is blended for maximum density and durability. These precision steel molds are oiled to ensure the concrete releases perfectly without any surface damage. Steel fibers are added to enhance the flexural strength of the massive concrete blocks. The concrete is poured while being subjected to high-intensity vibration to remove all air pockets. The hydration process generates heat, which is carefully managed to prevent internal cracking. As the mold opens, a perfect Tetropod block emerges with sharp, engineered edges. Each individual block can weigh anywhere from 5 to 40 tons, depending on the project requirements.
The water curing process lasts for weeks to ensure the concrete reaches the hardness of granite.
Every block is assigned a unique identifier to track its placement and long-term health.
Specialized transport vehicles carry these units to the harbor for loading onto heavy lift barges.
Loading the barge requires absolute balance to prevent the vessel from tipping in the open sea.
These offshore journeys carry the protection of the land from the ocean's relentless power.
Millimeter-precise GPS technology helps determine the exact drop location on the seafloor.
On site, male South Asian engineers are ready for the most complex assembly process in marine engineering.
Crane operators utilize sonar systems to see through murky water for perfect block placement. The first deployment begins. The massive concrete block slowly disappears into the blue depths.
The first Tetropod is placed, beginning the formation of the defensive foundation.
The interlocking design means that the harder the waves hit, the tighter the barrier becomes.
From above, they form a resilient honeycomb structure, capable of shredding wave energy.
This process is repeated tens of thousands of times to armor the entire seawall base.
Every batch of concrete is tested to ensure it can withstand the crushing weight of the ocean.
Efficiency is crucial when millions of tons of material must be moved in a single season. Sealants prevent salt water from reaching the internal steel fibers, extending the wall's life. Production runs around the clock to meet the urgent deadlines of the storm season. Construction is a race against time before the first major hurricane of the year arrives.
Advanced lifting gear is used to ensure the blocks are not chipped during the moving process.
Engineers continuously iterate on block shapes to find the best balance of weight and wave dissipation.
Textured surfaces help the wall integrate into the environment, becoming a home for marine life.
These next-generation units require less material, but provide even greater interlocking stability.
To provide a stable platform for lifting, massive jack-up rigs are deployed in the offshore zone. Every connection is double-checked. A failure here could result in the loss of a 40-ton component. The operator must account for the swell and movement of the sea while placing the block.
Divers ensure that the landing spot is clear of debris so the block sits perfectly flat.
High-frequency sonar sensors allow the operator to see through water with zero visibility.
The placement is managed by a sophisticated software suite that tracks every single unit in real time.
Once submerged, the block's effective weight decreases, allowing for more delicate maneuvering. Divers use physical guidance to ensure the interlocking legs of the blocks mesh correctly.
From the diver's perspective, the seawall is a colossal, silent mounting of stone.
Day after day, the armor is built, one 40-ton piece at a time, until the shield is complete. The sound of industrial tension is a constant in this high-stakes maritime environment.
The wall immediately starts providing a new habitat for local marine species.
Laser surveys are conducted above water to confirm the underwater placement is accurate.
In between the concrete units, natural stone is used to fill gaps and increase the total weight.
The random appearance is actually a highly engineered configuration to maximize wave chaos.
These sensors will record the impact force of future storms to provide data for future designs. The logistics of a seawall require a constant, unbroken chain of material delivery from the shore. The fleet is agile, moving to the next section of the coast as soon as a segment is finished.
The safety of the deep-sea workers is the top priority for the engineering company.
A single section represents months of work and thousands of man-hours from a dedicated team.
Some vessels can deposit thousands of tons of stone through a pipe directly to the seafloor.
Precision stone dumping is a high-tech game of underwater coordination and mapping.
Only the hardest rocks are selected to survive the constant grinding of the tides for a century. Remotely operated vehicles are the eyes of the engineers in the deepest and most dangerous zones. Construction continues even in rough weather to stay ahead of the critical hurricane season. Constant vigilance is required to spot incoming swells that could disrupt the heavy crane work. Stability is everything when lifting components that weigh more than a massive semi-truck.
High-resolution digital maps are created every week to verify the as-built progress of the project.
Nature is quick to reclaim the structures we build, a sign of successful ecological integration.
The foundation and armor are complete. Now, the vertical wall must be raised to its final height. Parallel to the stone base, the vertical concrete wall stands as the final line of defense. Inside the wall is a labyrinth of rebar, designed to resist both static water pressure and wave force.
Every steel joint is meticulously inspected. It is the soul of the wall's structural flexibility.
Concrete is poured in segments to strictly control the material's temperature and shrinkage. Climbing formwork technology allows the wall to rise daily with absolute vertical precision. The smooth surface reduces friction, allowing waves to slide upward rather than striking the wall head-on.
The bullnose curved design throws massive waves back into the ocean, protecting the land behind.
It is a brilliant design, turning the enemy's own power into a weapon of self-neutralization.
Expansion joints allow the wall to move slightly with temperature changes without cracking. Specialized epoxy sealants ensure the wall remains completely watertight, resisting every drop of brine. Drainage systems are designed to handle the massive overflow of rainwater and sea spray. Colossal one-way valves ensure that water from the mainland is always discharged safely. Nano coatings protect the wall from salt, acid rain, and environmental degradation for decades.
Behind the wall, life and commerce continue as if the oceanic threat never existed.
Beyond protection, Seawalls often integrate maritime safety and public recreation spaces.
Monitoring never stops. Every meter of the wall must pass rigorous pressure and density tests.
Emergency access and rescue infrastructure are installed to serve in critical situations.
When the first major storm hits, the wall proves the value of a multi-billion-dollar investment.
Every data point confirms the wall is operating exactly as the engineering geniuses intended.
This incredible contrast is the ultimate testament to the projector's total success.
Globally, engineering marvels like the Netherlands' Maaslandkering are protecting entire nations. These mechanical joints allow colossal gates to swing shut during the most dangerous North Sea storms.
In Japan, vertical tsunami gates protect harbor cities with the push of a single button.
The future of coastal defense is living sea walls, where biology meets industrial strength.
Modern walls are becoming energy hubs, generating solar and tidal power for the cities they protect.
Subscribe to our channel to witness more engineering miracles and industrial secrets from around the globe.
AI-driven maintenance ensures these structures remain invincible for generations to come.
Our Caucasian female engineering genius is redrawing the line between humanity and the rising tide.
The journey to protect our world never ends. Join us for the next episode of Engineering Brilliance.